Hello, everyone. My idea is to share and explain a few concepts, and then you play around with them, use the library, think about the models, and then we moved to some new content. We start with like continuous data, then minor data, discrete, and stuff like that.
Well, we would like to introduce you first.
Yes, but just that I have no slides. My idea is for you to be doing things most of the time for this session. So if you want to more or less tag along, I'd recommend like getting in groups along a table where you have someone who's following on the laptop, and you can look and discuss what they're doing and stuff like that. Otherwise, it will probably be a bit boring to stay here while I don't say anything and you don't have the laptop to also do things.
Okay, should we get started?
Welcome back, everyone, to the last session of today. Here's Oriol. He's a computational statistics working as a maintainer of ArviZ and PyMC libraries, and as a principal data scientist in PyMC labs. So in this tutorial, he's going to walk us through model with some full posterior predictive checks. So please welcome our speaker today.
Thanks. Nice. So yeah, my name is Oriol Abril. I'm one of the maintainers of ArviZ and PyMC libraries, if you're familiar with them. I mostly work on ArviZ, not so much on PyMC, but also a little bit. And my tutorial today is to use posterior predictive checks to inspect different types of models. So I'll start with a bit of an introduction. In the meantime, if you can start, you should have the link to the repo in the here, GitHub. So it's Oriol Abril, Pydata 2026 PPC. If you don't have access to the slide, and it should be easy to clone because the notebooks are empty and there's no data. The data is generated later on, which hopefully helps things along. If anybody has any issue, please let me know. And we also have support tagging along. I have set up Pixie so that it's easier that we are all running on the same environment, because I'm also running this on a branch of ArviZ that I haven't yet actually even merged into main, much less released, so that we can do fancier things when it comes to posterior predictive checks, groupings for continuous variables that have hierarchy, categorical splits, and things like that. Has anybody been able to do this successfully? Not yet. Okay, so I'll wait a couple minutes before starting. Yes. Are you being able to follow? Yes. Thank you. So we have some yeses. Still nobody complaining. So hopefully good news. Yes.
Can I just ask a question? I've never seen Pixie before. Is it like better than Task or Make? Why did you go with Pixie?
I used Pixie because it can handle both conda and pip dependencies, and most of them are installed via conda. This environment doesn't have PyMC, so it probably wouldn't matter that much, but I'm used to having a lot of issues trying to install PyMC with pip, so default to conda when possible. Okay, so let's get started. As I said, we'll be focusing on posterior predictive checks. We'll be doing that with ArviZ, which is a library for what we call exploratory analysis of Bayesian models. So the idea is you build and you feed your models with PyMC, with Stan, with NumPyro, TensorFlow probability, whatever you want, and then you can load these results quite easily into ArviZ. And we have functionality for model comparison, inference diagnostics, uncertainty visualization, model criticism, which is what we'll focus on today, and stuff like that. So the talk has a very big component of ArviZ showcase too, and that we recently released a major version. So there are many new features. Many of them are related to posterior predictive checks. So if you have already used ArviZ, I don't know if anybody has already used ever Stan, PyMC, ArviZ, to that a little bit. So there are particularly in the posterior predictive, but also we have a lot of new checks for prior and likelihood sensitivity that can tell you how will the model inference change when you change the likelihood or the posterior or the priors of your model without actually having to refit the model, which is quite handy. And so we start with the posterior predictive distribution. In the Bayesian models, when we fit our model, what we are actually trying to find is what we call the posterior distribution. That's a distribution over all the parameters in our model that gives the full picture with uncertainty, point estimates, and everything, not only a single value. So we can know also correlations, all the different relations between the different parameters, which ones we are more sure about the value, which ones we have more uncertainty, and so on. Then we can take this posterior distribution and take it one step further by combining it with the observational distribution or the likelihood in order to generate predictions for which we'll also have a full distribution over our predictions. This is what we call the posterior predictive distribution. In practice, how does it look? So we have n realizations of our posterior samples, and then we generate one sample using the observational distribution so that we have n realizations of our posterior predictive. Here we have some examples from ArviZ that you can look at. You can see that we store a whole lot of things. Today, most examples you only have posterior predictive and observed data, but in general, this will come from fitting a model. So you'll start with posterior, then you can have sample stats, evaluations of the log likelihood, also prior samples, observed data, constant data, stuff like that. So basically, our data, we start with this observed and constant data. So here we have 919 observations of random concentration measured around different places in Minnesota. That's the random, yeah, not particularly relevant, but so you know. Then we have a model that has some regression components. We have parameters that are coefficients that depend on the county the measurement was taken in. We have an intercept, we have a slope, and stuff like that. And out of this posterior, for which you have chain draw, so 2,000 samples for each of these that describe a distribution. If we look, for example, at the G, so this is what it looks like when we plot the marginal distributions over all the samples that we have for this variable G. And then we do this small forward sampling step so that we get posterior predictive distributions out of this posterior. So we end up with an array that has this chain draw upside D shape. That means that we have 2,000 realizations of our posterior predictive, which are 2,000 ways our model believes our data could look like. And the base of our model criticism will be based on this. We have a model that is capable of generating what the data would look like, and we have already fit it, so it should look very similar to what our data actually look like. If it doesn't, it means the model is missing something. Yes, any questions about conceptual framework, what we have, what are our model outputs? Good. I have another example that is a bit more complex models. In this case, we have observations, 2 variables. This is from results of the 6th Nation Championship rugby competition. So we have the points that were scored by the home team and the points that were scored by the away team for each of the matches. And that means that when we generate this posterior predictive that's down here, we also have similarly looking data, but with the addition of the chain and draw dimensions, because we have the full draws from this posterior predictive distribution. Yes. So the first thing that can come to mind is I now have 2,000 realizations of our simulated data. I can take the mean of these 2,000 realizations and compare these means to the actual mean of my data. So the mean of my data is 125, and I have 2,000 values that you can see more or less are not that far from here. So I can plot this manually. Like first I plot the distribution of these 2,000 mean values of my posterior predictive, and then I add a reference line for the mean over the observed data. And we can see that for this radon dataset, it matches quite well. We have this function called plot ppc tstat, and you can choose multiple t statistics, median, mean, interquartile range, standard deviation, median, absolute deviation, different quantiles, stuff like that, so that you get more or less the same plot but focused on this. So this is the distribution over the posterior predictive for this t statistic function, and this is the same t statistic function applied to the observed data. We have a function to combine plots all applied to the same data, so I can compare STD, median absolute deviation, interquartile range all at once. And we see that more or less all look okay. But this has a lot of limitations because the mean, more or less, the deviation can look okay, but the shape of the distribution can actually be different from the actual shape that we have in our observations. So what we usually fall back to is comparing marginal distributions directly. So we take the posterior predictive and then we overlay samples for each chain and row combination. So we'll draw 2,000 lines, one over the other, generating these marginal distributions over the whole observed space. And then we'll do the same. Here there's no overlay because there's only one, which is the actual observations, and I'll put it in black. This takes a little bit because we are generating 2,000 KD lines with Matplotlib, and this ends up looking like this. Again, we probably don't need 2,000 lines. With 100, 200, it's more than enough. So we have this plot PPC dist that is focused on these kinds of comparisons. And here the idea is that you, as an analyst, should not be able to distinguish this black line for anything else than the fact that it's black. So let's show an example. Here I have loaded multiple models. Only one is good, the other three are very bad. So if you look here, in the proper fit, the line is now blue, and it's very hard to guess which one is the line that corresponds to the actual observations. It's fused with the lines that correspond to the model realizations for the posterior predictive, whereas for the undispersed, there's this line down here that is a bit of another one out. For the over-dispersed, this one is clearly a different one, and it doesn't make sense that the model is generating 1,099 realizations that look the same, and then one, for no reason, is different. So this is our observation, this is also observations, and this is because this model is under-dispersed, so all the realizations of the posterior predictive are thinner than the actual observations. This one is over-dispersed, so the opposite situation, and this one is biased. If we look at this in the KDs, it's nice to look at because as humans are very good at processing graphical information, particularly if lines are smooth, it's very easy for us to see which line corresponds to what. Even though this line is crossing through here and it has the same color, it's relatively easy for us to parse that this line goes down here and it's the same as this other one. When we add the extra color, it's even easier, but this is not the case for everything. We try to prefer these KD or ECDF visualizations, whereas the dot and the histogram visualizations, while also very good or even better when you're looking at the uncertainty distribution for a single parameter, not overlaying things, they don't serve very well in this context. But it serves to show how these different plots look for these different problematics. So now you can see in black the under-dispersed, over-dispersed, biased. When you look at the empirical cumulative density function, you can see that it's flatter. Here it's more steep because it's over-dispersed, so the observations go faster from having no mass, no probability mass, to having all the probability mass, and the bias is simply shifted, whereas these two are interpreted more or less the same as the KD, but the histogram can be a bit hard to read because all the lines are squares, so it's not that easy to know which actually follows from the other. If we look at this from the t-stats, and we focus on measures of deviation. We looked at the biased model. What do you think will happen? If the model is only biased and we are measuring the dispersion of the model predictions, it will look like the model is actually good, because the dispersion is not the issue, it's the location. And you can see that indeed it looks quite good, whereas if, for instance, we change to one of the under-dispersed or over-dispersed, here we'll see that the model, all the posterior predictive realizations of our observations have way lower STD than the actual observations, lower median absolute deviation, and lower interquartile range. And we could generate always like multiple views of dispersion measures, and then we also have centrality measures. We could add other moments and stuff like that, but all of this is straight to see. Yes?
So for the cell graph for the estimators, KDE, I think is like
Kernel density estimator. ECDF is empirical cumulative density function.
And then there is also
Dot is the quantile dot plot, and histogram is the histogram. The quantile dot plot is kind of based on the empirical cumulative density function. So you take n quantiles out of your distribution, and then you assign one dot for each with a given width. So if the dots are close together and they overlap, you stack them all together at the same location, which is in the middle between all the quantiles that overlap. If there's only one, you have one here, then the other, and so on and so forth. The nice thing of the dot plots is that if you want to know what's the probability of this value being larger than 2, and here we have, I think, 100 dots. We have one dot over here, so it's 1%. Smaller is 99, and you just have to count the dots in order to compute probabilities for different ranges. Yeah, and here with the bias, if we use the centrality measures, they are now all off. The mode is not that off, but a little bit. Yes, more or less so far. Another issue we might have is that here we can get a lot of lines overlaid. We can also have models that have larger dispersion of the predictions per se, things that look wider, or there's more differences between the different realizations of the posterior predictive. So something that is also very common and that we use a lot in ArviZ is the probability integral transform. I don't know if anybody is aware of this rule, but basically, if you compute this quantity, which is the probability or the percentage of posterior predictive samples that are lower than the corresponding observation, which is a scalar, because we are focusing on each of the given observations, this will have a uniform distribution. And that's a rule of statistics. And so here is how we would compute it. So we take posterior predictive, smaller or equal than observed data. Then we take the mean over chain and draw. And then if we plot the distribution over all the different observations that we have, this will be more or less a uniform distribution. The main caveat that you will see is that, yeah, this looks kind of uniform, but how uniform is uniform enough? And this is what we'll address later in the plots, but you can see that if we use, for instance, the over-dispersed for this kind of thing, it will be very clearly not uniform. And we can see that indeed this is very clearly not uniform. Why? Because the posterior predictive is over dispersed, so the probability of this being smaller than the actual observed data is not properly calibrated. So we'll have way more values around the center than we have in the tails. This we have incorporated in this plot PPC pit, where what we actually do is we use this ECDF visualization. We build the ECDF for our pit transform, and then we compare the ECDF to the ECDF of a uniform variable, so that we get the differences between the ECDF that we have actually obtained and the ideal ECDF. So instead of seeing this kind of increasing shape, we'll see a straight line and the differences overall. And for instance, for the under-dispersed, it looks something like this. When there are clear issues, this is off the central line, and how far away is bad enough. We have a p-value, even though we are Bayesians. We also use some frequentist estimates, and we highlight in red the values where this deviation from the ECDF is more problematic. Yeah. Here, if we take a look, you can see that for the, this is the over-dispersed, right? No, under-dispersed, sorry. Yeah, so under-dispersed, we have the ECDF over and then under with respect to our predictions. So that's why you end up with this N shape in the ECDF difference. I always forget when the N or the inverted N is over or under, but you generally get these kind of shapes. Yes?
Why do you think it's more problematic there and there?
Sorry?
The orange markers.
The orange markers are the observations that contribute the most to the ECDF being off the ideal ECDF. So it's not literally the one that is farther away, it's the ones that make the most contribution to the p-value actually breaking the constraint that we care about. We have multiple methods to compute these kind of things, but they are used for slightly different scenarios. This one is the better default in general. And anybody wants to venture a guess about what will happen when we generate this difference between ECDFs for the biased? If we go back and look at this, at the biased, what's happening? Yes.
Would you have a bunch of red dots, like not very many red dots at the beginning, and then it would be really far off, a bunch of red dots, and then not very many at the end again? Like, are you basically looking at the place where, from what I'm understanding, the red dots appear where that line is most egregiously outside of all the other blue lines? Right in saying that?
More or less, okay. Yes. But excluding the red dots, like what will our blue line look like? Yeah, so it will, if you look here, this is always above or below. So we'll have kind of a U shape where the difference is always on one side of the ideal little line. Yeah. So in many cases, we won't have such dummy scenarios, but we'll have data, and I can actually show this to one or yes, we are modeling all of these as observations, but the observations might have categories A and B that might behave slightly different. In this case, they don't because this is an example, but they will. So we might want to check not only the global fit, but also the fit for each of these particular categories. So for plot PPC dist, this is one of the functions that we use the most. So you can just say calls equals category, and you automatically get these two views. And here we have a finer line because we have more values. Here it's a bit coarser because this category has less values. We also haven't changed the kind from KDE to ECDF, but we have some defaults that if the number of values in one of the plots is too low, we shift off from the KDE as default and switch to the ECDF. We also have many plots where things are not as advanced as this. Hopefully will come soon. So what we have to do is kind of promote these different categories to their own variables. So here, instead of one dimension of 150 length, we have now one variable with item A dimension with length 100 and another variable with length 50, and then we can use this same kind of idea to generate two plots with the PPC pit for each of the categories independently. And now it's playground time. So there are more sections to come. I'm not sure how, yeah, we are good on time, I think. So now the idea is for you to take the notebook, load these two examples, play around with all the functions we have seen, t-statistics, pit, ECDF, raw marginal distribution comparison, and find the issues with this data, or say, this one looks good. So I don't know. I'll give you at least like 3-5 minutes to play around, and then you can tell me, I think this plot really shows the issue with this model or that other model, and I will reproduce it here for everyone else to see. And if you have questions, I can also move around and come to you. To go a bit quicker, we also have this version that does the pit and the dist side by side without needing to go through combined functions. When we do this with the first example, things look good. When we do it for the second example, things don't look as good in the ECDF, but if we look here, it doesn't seem so problematic. So there's probably something a bit funky going on because this is mostly under and it does a bit of this N shape. So we probably have something that's both biased and under over dispersed. But it's not super clear that is actually happening when we look here, maybe a bit under dispersed. But if we look at the why is it breaking? Hey. if we look here, this is looking not so good, particularly this one, but it's still not super clear to see that there's actually an issue, even though the ECDF bit is clearly showing that something wrong. So we'll apply this to this DTX2. And then it's I forgot to remove this. Yeah. And here we can see that indeed both categories are slightly biased. Yes. Yeah. So when you look at these ECDF difference plots, the magnitude itself usually doesn't play much of a role. That's why we have the p-value and the red dots. There is also an envelope which looks very nice, but it has some issues because it doesn't account for the autocorrelation in the samples. But this hopefully will be fixed in a couple papers. And now it's not working. Okay. And this gives an idea of the magnitude that things should have, because it depends a little bit on the variance and the different things. Yeah, okay, and it has an issue, but it's deprecated, so probably will not fix it. And if we look at the same for the one, we could see that overall for the one in the global it looked very good. Nearly perfect fit, but this is actually all due to the A category, and the B category is terrible fit. So both models have issues. One is global issue that nothing is actually matching, but it's hard to see if we are only focusing on t-stats or raw overlaying of densities, and the bit check really comes in handy. Whereas for the other one, both the bit check and the overlaying look good, but when we look at this at a category per category basis, we can see that our model is either assuming that category B has some difference that are not actually there, or vice versa. Our model is assuming everything is the same. We have more values in category A, and so we only actually fit category A. And here we would have to either improve the model to take these differences between categories into account, or remove category B observations and focus that this model is good for category A. We'll focus only on these types of values, and that's what we can do for now. Yeah. The bit check will also work for discrete variables. The overlaying with the ECDF will also usually be helpful, but KDs don't make sense. Histograms and dot plots, when overlaid, are usually not that helpful. So when we try to use this for binary, for discrete data, for other kind of things, we have to think of other strategies to compare our posterior predictive with our actual observations. And if we start with binary data, so here we have 374 observations. And for binary data, the main thing we'll focus on are calibration plots. So the gist of the idea behind calibration plots is we want, for the group of observations where a model predicts low probability of success, to have overall low probability of success in fact. So for instance, we can take the means of our posterior predictive, and see how they look like, and then we check the observations where this posterior predictive mean is under 0.1. We have 373 observations, but when we filter only those where the posterior predictive gives less than 0.1, we end up with only 59, and then we can take the mean of that, which would be 0.01. We can do the same for larger than 0.9, now it's 98, and we take the mean, and now it's 0.91, and if we do it for between 0.4 and 0.5, ideally what we expect to happen is to have a value between 0.4 and 0.5, and this will be an indicator that the model is actually calibrated. Yes? Makes sense to everybody? And in fact, this model is quite good. In ArviZ, we have plot PPC Papa function that takes this idea and builds on it through several papers to both make it more robust and also adapting to these kind of comparisons with Bayesian results, where you have the distribution for the posterior predictive and the observations and so on. So there are a couple extra twists, but the intuition is the same. We want this diagonal line for our calibration to be good, and we will just build an extra envelope and so on. The left side are these conditional M probabilities, which is kind of like the equivalent of doing this kind of thing, but there is no binning involved, so it's more robust. And we are also able to generate this band of confidence. So the fact that the blue line is always inside the shaded area means that our model is properly calibrated within the accuracy that we have. Yeah. This same idea we have focused like between 0 and 1 because this is a binary model with a probability, but we could do it for a discrete model and values between 4 and 10 or 20 and 35, and we apply the same kind of checks to look at calibration of discrete variables, and we'll also see that it works for discrete variables. Some extra playing. This is so I added some models. Now there's only plot PPC Papa to use. So there are more examples, but should hopefully also be relatively quick. And yeah, we are not super bad on time. So. Let's play around a little bit, and for those of you that haven't installed things, you can also propose for me to do things, then I'll show it and you can interpret it, see what you think. Here there isn't much that we can do other than running this. This one looks quite good. It's a little bit off here and there, but mostly within the shaded area. That means that it's somewhat well calibrated. Second example. is a disaster. It's mostly outside of the shaded area, so this is bad. The fact that it's above, again, I'm always messing this up, but it means that we are predicting a 0.3 probability of success for this block of observations, whereas we are actually observing a 0.5 probability of success. So we are under predicting significantly the Bernoulli in our model, or the logistic regression, or whatever you are actually doing. Something that is also relevant is this now finishes at 0.6, not at 1. This is because this model is under predicting so heavily that the highest probability of conversion that it actually spits out is 0.6. So the bar cannot go above this, and the axis in this plot will be the minimum maximum of the success probabilities for our predicted values and for observed values. If we apply this, as we will do later, to discrete data, the minimum maximum will be if it's negative binomial or something like that, the minimum and the maximum of the values that we can take, and it will ideally be a straight line between them. If you have very, very good models where the deviation is only around 0.5, 0.45, 0.55, something like that, I don't remember if I have an example for this, but you can end up with something that looks like a flat line and then some spikes to the top and to the bottom for the shaded area. The fact that it's not diagonal is not an issue as long as it's within the shaded area, because we are just restricting the ranges, especially on the x-axis, where the y-axis, due to the bands particularly, is still much wider. This is the opposite case. Now it starts at 0.4. We are under predicting and finishes at 1 for the 4. It is quite off, but we are both here over predicting, but then here under predicting. So it's not one single issue that breaks everything, but multiple things that are going wrong at the same time. And this is one of the examples where we have indeed this from 0.58 to 0.62. So it looks very flat. This one is mostly outside the shaded area, so this is not properly calibrated, whereas the 6 is also super flat looking, but within the shaded area, so this is very well calibrated, even though it doesn't look like a diagonal line. That's mostly an artifact of the plot, because this is 0.45, 0.14, 9, whereas here is from 0 to 1. If we added this axis to be from 0 to 1, it would look like a dot, but if we zoomed in, it would eventually kind of look like a diagonal line too. Yeah. Okay, so then we jump to now discrete data. So we start again with the rugby data set, and the first thing that happens when we try to use plot PPC dist is that we get a warning that tells us to either use plot PPC PAVA, which we have just discussed, or plot PPC rotogram, which is another visualization geared toward discrete data. If we look at the KDE, it's the code works, but it's a disaster, way too wobbly to take anything out of it, because the KDE is kind of smoothing. But here we have values at 10 and 11 and 12, but nothing between them, which kind of breaks the assumptions of the KDE that builds like Gaussian kernels around the observations, and the histogram is also somewhat hard to read, whereas the PPC fit is, again, still a nice visualization to look at. And here we can see that, for instance, this is probably the model is under dispersed because the black line is wider and has more mass towards these edges, whereas this is more spiky. And we get this seen more easily here. And we'll also see it a little bit in the rotogram. So the rotogram is a bit of a mix of different concepts that we have already seen, mainly the t-stats applied to, we have a finite set of available values, so we'll just run t-stat comparison through all of them and see how things fare. So basically, here we have values that can be from 0 to 60, but that means we have 60 possible values, not infinite. And if we take a look at what is the count of values that are exactly equal to 20, and we compute this for the posterior predictive and for the observed variables, we get something like this. If we do this more manually and we plot the whole distribution with the intervals and the point estimate and so on, and then the observation instead of a dot with the line, we get something like this. So for the rotogram, we'll take this reference line and then these credible intervals in order to build vertically the result of this for each of the possible values that we can see. So we'll do this for 1, 2, 3, up till 60. And eventually it will look like this. So we were at 20, and we can see that the observation at 20 is at 5. Yes, it is at 5, and we have the interval from 5 to 0, which is indeed the case. And here, for the away points, we have the observation at 2. So 20, observation is at 2, which is this one, and the interval is also from 5 to 0, which is, again, the case. We do this for all the points. And then here we can see that we have a lot of observations with high values for low points, whereas the model doesn't really catch all of this. And we set the axis to the square root so that it's easier to see the differences for the small frequencies, which is usually not such of a problem for high frequencies. And that's eventually what it looks like. And here the main goal is to hopefully get all the dots within the bands at least, and more or less following the shape of the posterior predictive means. And again, we can also use plot PPC power, which now goes from 0, 10 to 60, matching the range of our actual data. And we can see that it's not bad, but there are several areas where we are over predicting. Around 20, we are under predicting this amount of points being scored, whereas for 10, we are over predicting this amount of points being scored, and so on. Yep. Still feel like playing? Yeah. We are good on time, so now we have a lot of plots to try. Yes?
Would you use the same thing for like multinomial where it's not orders? So like a dice or something?
Yes.
Not 5 and 6 following.
Is so As long as it's discrete data, yes. If it's categorical, then we would use a variation. The rootogram wouldn't be useful in that case, but we can use a variation of plot PPC Papa. I don't have a particular example for this, but it has this argument data type, I think. Yes, data type, which can be data type, categorical, or ordinal. And it will adapt the PPC Papa. The main idea is that you'll do like one category versus all the others, check the calibration for that, then jump to the second category, calibration of this category versus all the others, and this way you can still define this kind of category in the sense that we are predicting this observation is that category. Is it, or is it one of the others? And that's what still allows you to build the multiple plots. The main issue is that if you have a lot of categories, you'll have too many plots to look at. So you might want to start with a confusion matrix and then generate the calibration plots for the problematic ones, something like that. So these CRAPs are two models fitted on the same data, and it's usually what we use to showcase the rootogram. So plot PPC rootogram, CRAPs Poisson. We see that we are predicting way too many values around 1, 2, 3, but at the same time we're predicting way too few for 0. So they changed the model to, instead of using a Poisson likelihood, to using a negative binomial with a hurdle for the 0. And it's still not ideal, but it is now much, much better. So now we do match the predictions for 0, and the others look good. The 2 is still of a bit of an odd one out. So people who know about CRAPs would have to look at what's actually happening, and if there's something else to explain, maybe a mixture of behaviors, something like that. If we do this for the examples, this one doesn't look very bad, but there are multiple places where it's a bit mismatched. So this one is off the bands. These ones are nearly off the bands, but in general it's okay. The main issue here is when we look at this is probably the quicker way to see this. We have categories also for this model, and here the overall fit is good. But when we look at specific categories, it's a complete disaster. And we are under-predicting for attackers, over-predicting for defenders, goalkeepers, midfielders, and so on, because we are assuming that everybody has the same behavior, which is not the case. And this is mostly fixed for the DT, the 2. This one looks a bit better, but is also struggling with this one. And if we do the same here, we'll see that now it matches a bit better, but the defenders are still a bit off. And we can, for instance, have it here. The exploding of things, yes. Goalkeeper is also a bit off. Defender is very off, but these two are quite good. And now it's complaining because goalkeeper only has 0 or 1s. There is no goalkeeper that scored 2 goals during the season, so the bit is not very appropriate to actually use for this kind of check. And we can look at the PAVA instead, which will work for both the binary and the discrete versions. And not so bad. Yeah. And if we looked only here, we probably conclude that this is not very problematic. But if we look at the other plots, that's why we need to look at multiple ways to compare the posterior predictive and the observations to see different kind of issues that can arise with the model. Okay. Now there are no more extra fancy plots. It's just a plot that you probably all know already. But in addition to all the plots that we have seen that will apply to the kind of regression we're doing, if it's a logistic regression, then we cannot use the rotogram, but we can also use the plot PPC PAVA. There's also a plot PPC PAVA residuals function that is designed for kind of binary regression type of models. But in general, when we are doing regression models, what we will want to do is the plotting of the observations and the posterior predictive as a band over those observations. So this is, I think, zero inflated negative binomial regression. And the default is for ArviZ to generate this kind of plot with plot.lm. The dots are the observations, the line is the mean of the posterior predictive, and the band is a credible interval for the whole posterior predictive. And we can choose which variable is at the x. We can do some faceting, map colors, map multiple stuff. We can also define multiple probabilities for the bands, in which case they get mapped to alpha, so you can distinguish them more easily. And here it looks like this. These are equal tail credible intervals. So the inner one is the 50% probability. That means from the quantile 25 to the quantile 75, like the interquartile range. And this is the mean. And this is clearly a skewed distribution, so it's nearly off this interval, because this is not the median, so it doesn't need to be in the middle of this band at all. And we have some more extra models to play with, see what happens. You can generate these kind of plots to get a bit of an idea what data looks like, but in general, these plots are more of an orientation to see, like, is it fitting the different categories more or less good enough? Is the data in the range that I would expect to see? Are the posterior predictive bands going under 0, which would make no sense in this kind of count model, things like that. But to find actual issues, it's very hard to see here. Is this properly calibrated? Should the band be higher because this dot is very far away? Because we have so many dots here overlaid that the band is 90%. Do we have 90% of the dots here overlaid, or are these too many dots outside the bands? That's very hard to see, so you have to combine it with all the other types of visualizations that we have been looking at so far. And now you have more data to play with. 15 minutes only left. Hopefully you had some time to play around with ArviZ. this is mostly focused for Bayesian models, but as you have seen in the examples, we only used observed data and posterior predictive. So any model that is able to generate predictions for observations in a probabilistic manner is a good fit for all these kind of checks. This is just mostly a way of thinking probabilistically about how to interpret results and compare to single observations. And so yeah, play around a little bit, do ask any questions you might have, and in 5 minutes or so I'll show some extra plots generated out of this. I added some references on the different notebooks. The main ones is this, which is kind of like an online book that we have explaining the concepts around ArviZ, not so much the ArviZ actual usage. And then here, if you work a lot with regression models, you might be interested in checking this Bambi library out, which is a library that allows using R, Patsy-like formula syntax to generate full Bayesian models that you can then fit with PyMC. So you get full posterior predictive, log likelihood, stuff like that. Yes.
Would you ever do these plots versus like unseen data rather than observed data? Like in sort of non-Bayesian stuff, you'd have a test set, train set, and you'd fit on the train set.
Yes, yes. So we do have some of this already implemented. The most common way to do this kind of thing is through live well out cross-validation. For these models, as they are Bayesian, we can compute the log likelihood that our model gives, and we can actually use this log likelihood to estimate what the leave one out prediction would be without having to refit the model. So we have this, I think for the red one we have it. Let me check. Log likelihood, yes. So here, no, not PPC, blue bit, yes. So this is the same concept as the PIT check that we have discussed, but here, instead of comparing the, where did I, in the middle of the notebook, yes. Instead of comparing the posterior predictive conditioned on the full fit of the model, which is a bit of double dipping, we are comparing this to the observation Y, but conditioned on the fit that excluded observation Y. So we fit on everything but this observation, we generate predictions for this observation, and then we compare to the actual observation as a holdout. And we repeat this for all the 900 observations that we have. The good thing is that we can approximate it. So instead of having to refit a model with MCMC 900 times, we get nearly instant result. But you can see that it looks very similar, but it's not the same as the not exactly the same, because this is not doing the holdout, this is doing the holdout.
Which one's more valuable out of the two?
I mean, this one is conceptual a bit more sound, because you are not doing this double dipping. Given that you're using the full distributions from the full posterior, a bit of double dipping is usually not a big problem. But if you can do it more or less cheaply, you can go out of plot loop it. But this relies on this being able to compute the pointwise log likelihood evaluations at each of the data points for each chain and draw and so on, which depending on the model is not available. Any more questions? Has anybody ever used something like this? Thinks they could use it? Maybe? Hopefully. Okay. So for these first two examples, we have two independent variables and a single dependent variable. And if we do at the plot lm, we get this kind of strange shaped because we are plotting only against x, but there's also a z variable that modifies, in this case, only the mean of our regression. So we are not accounting for that. So every x will have a random z that makes it look a bit funky. If you want proper interpretation plots, it's easy to set them up through Bambi. Otherwise, here you'd have to fix the x, generate posterior predictives for all the x's that you have, and then generate the plot with the constant z, but then it will not match exactly any of the axial observations. So it's tricky to compare back and forth. The x is the first variable, so it was used by default. But we can set the z, and it also looks a little differently. If we look at the second example, it's actually even worse, because now the dispersion of our regression, the sigma, also depends on the x. So here it's like randomly increasing and decreasing, and if we set the x, it decreases as the x increases, while the mean continues to depend on z. And the good part is that if we do like plot PPC pit, all of this is abstracted away because we are comparing each observation to the respective posterior predictive comparisons. So we just get the plot automatically, and all of these differences in the independent variables are thrown away. But if we look at the distribution, it will probably be like wider thing with a strange shape that we don't recognize and doesn't match the likelihood and so on, because we have y whose x and z are all around the place, kind of mixed together. And for the other one, we only have one independent variable and one dependent variable. We have multiple groups, kind of, and the groups can define the slope, the intercept, and the sigma of the regression. And we have this defined as a 4-dimensional array. So now posterior predictive has chain, draw, group, and ops ID. And by default, what ArviZ will do is, where is it? Facet along the group dimension. So we now end up with 5 plots, 1 per group, where we compare the y of the A group to the x of the A group. If you want to see this in the same context, then we can do calls to not be mapped to the group anymore, and then we map the color to the group, for example. And the bands are mapped correctly, but the aesthetics map to the different visual elements depending on our settings. And this is probably a very bad setting, but by default, the line is not mapped to the color or to anything. So I'll say that I also want to overlay the min line depending on the group, and then as by visuals. What is it, the name? P line. If I only say overlay here, it will be overlaid instead of assuming that all of this is the same line, which kind of links them together in a crazy way. And if I say color, it will also take the color, so we cannot see it anymore. But again, we can generate this as a global summary or per category. And I think that's the time. Yeah, more or less. Any extra questions? Did you more or less enjoy the session? I'm used to much smaller crowds, and I go around and look and make sure they are following along in the exercises, which here was a bit too challenging, but hopefully I warned you enough in the beginning that you were expected to do a lot of the heavy lifting. That's all from me.